Hello and welcome to part 2 of this video playlist about the preparation of nitriles by alkylation of cyanide. This presentation is about the alkylation of cyanide with epoxides. This is an important reaction because epoxides are readily available and the resulting beta-hydroxynitriles are valuable intermediates for various applications. Because I already discussed most fundamental aspects of nitrile chemistry in the first video of this playlist, let's jump directly to the examples. Simple alkyl epoxides readily react with cyanide, usually at the sterically more accessible carbon if the reaction conditions are alkaline. Under acidic conditions, a reversal of regioselectivity is sometimes observed. If no buffer is used, the reaction mixture will turn strongly alkaline, what can cause dehydration or hydrolysis of the product. If an alcohol was used as a solvent, ethers from the solvent and the epoxide may be formed. Better results can be achieved with a buffer, such as sodium bicarbonate, as shown here. If the starting epoxide is sufficiently soluble, aqueous or protic solvents can be used for these reactions. Beta-lactams and silyl ethers may remain unchanged, as in this example. Despite the basicity of potassium cyanide, no beta-elimination of the silyloxy group occurred here. Because of the low solubility of alkali cyanides in organic solvents, nucleophilic cyanations of lipophilic electrophiles sometimes proceed only slowly, as in this example. Here, a mixture of water and acetonitrile was the solvent, and despite being a tertiary electrophile, a high yield of beta-hydroxynitrile resulted after refluxing for 3 days. A much faster ring opening could be attained with cyanodiethyl aluminum under aprotic conditions. Here, a quantitative yield was achieved in only 15 minutes at room temperature. These two reactions also show the strong deactivation of ionic cyanide by hydrogen bonding with protic solvents. Trimethylsilyl cyanide can also be used to cleave lipophilic tetraalkyl epoxides in aprotic solvents. Instead of the alcohol, the corresponding trimethylsilyl ether was obtained in this example. The reaction proceeded with high regioselectivity because direct substitutions at cyclopropane ring atoms do not proceed readily and because cyclopropanes stabilize carbocations like alkenes or arenes. Also, epoxides containing additional electrophilic sites sometimes yield products with high regioselectivity. One important case is epichlorohydrin. Unfortunately, the reaction of epichlorohydrin with an excess of alkali cyanides gives product mixtures. High yields of 3-hydroxyglutaronitrile can only be obtained by carefully controlling the pH of the reaction mixture. Moreover, in the presence of bases, epichlorohydrin can polymerize. Better results could be obtained on a large scale by conducting the reaction in 2 steps. First, a preparation of 4-chloro-3-hydroxybutyronitrile by single addition of cyanide to epichlorohydrin, followed by treatment of this product with aqueous sodium cyanide. The first step succeeded by dosing both epichlorohydrin and hydrogen cyanide simultaneously to the buffered reaction mixture, as shown here. Thereby, the polymerization of both starting materials could be prevented, and the heat generation was easier to control than in previous procedures. With highly reactive epoxides, better results may also be obtained by using trimethylsilyl cyanide as nucleophile, as in this example. Here, many products were possible, but under optimized conditions, only 2 main products resulted. The sharpless epoxidation enables the preparation of enantiomerically pure hydroxymethyl epoxides from allylic alcohols. The reaction of these epoxides with various nucleophiles has therefore been investigated extensively. Unfortunately, under most conditions, the addition of cyanide yields mixtures of regioisomers, as in the 3 examples shown here. The main isomer is usually the 4-hydroxybutyronitrile. Best results can be attained in aprotic hydrophobic solvents with trimethylsilyl cyanide. The acetylated hydroxymethyl epoxides gave still better regioselectivities than the non-esterified hydroxymethyl epoxide. Aryl epoxides often give high regioselectivities upon treatment with cyanide, but not always. In this example, an almost equimolar mixture of both isomers resulted upon treatment of styrene oxide with trimethylsilylcyanide. In the presence of an excess base, though, cyanide cleanly adds to the sterically more accessible methylene group of styrene oxide, as shown here. Substituted aryl epoxides react more slowly with alkali cyanides than styrene oxides. In this example, the reaction was conducted in aqueous methanol in the presence of ammonium chloride as buffer, but required refluxing for 2 days. Acceptor-substituted epoxides often react with cyanide at the carbon atom more distant from the electron-withdrawing group, as in this example. Here, a weak Lewis acid was used as catalyst. Cyanodiethyl aluminum can also bring about the ring opening of acceptor-substituted epoxides. Again, the reaction proceeded with high regio and stereoselectivity. Catalysts have been developed that enable asymmetric nucleophilic cyanations. In this example, cyclohexene oxide reacted with trimethylsilylcyanide in the presence of a chiral titanium complex. The expected nitrile was obtained in high yield and with good enantioselectivity, along with 8% of an isonitrile. So, what can go wrong? As we already saw in the previous example, one potential byproduct are isonitriles. Even terminal epoxides may yield these byproducts. Isonitriles result more often under acidic conditions and with SN1 type electrophiles. Isonitriles may even be the main product formed, as in this organic synthesis procedure. Simple aliphatic nitriles are quite resistant to attack by nucleophiles, but intramolecular catalysis or nucleophilic attack can enhance the rate of such reactions. Here, for instance, a complete hydrolysis of the intermediate nitrile occurred, probably by transient formation of a 5-membered cyclic iminoether. One further potential side reaction is dehydration of the initially formed alcohol. In this example, the main product was formed this way, despite the use of a buffer. If an excess of cyanide is used, the dehydration product can even alkylate one further equivalent of cyanide, as shown here. Although the intermediate Michael acceptor was sterically inaccessible, a high yield of succinonitrile resulted after only 3 hours. Here are some more examples. You can also find these references in the description of this video. The next video of this playlist is about the alkylation of cyanide by alkenes. Most examples are Michael additions to electron-deficient alkenes, but with the aid of nickel catalysts, also unactivated alkenes can undergo hydrocyanation.